let's talk about limits that do not exist. So here I have like the first picture you ever see in Calc 1 of a limit that fails to exist. The limit as you approach x naught from the left is different than the limit as you approach x naught from the right. And if we were to try to picture the two different ways to get to x naught in the domain, it would be really boring, right? Because you're either coming from the left or coming from the right. And one of the most famous theorems in Calc 1 is that the two-sided limit, the limit as x approaches x naught, exists if and only if these two one-sided limits agree. And of course, we all know there are other ways for limits to fail to exist, right? We could have asymptotic behavior, where maybe my function was growing infinitely as we approach x naught from either side, or minus infinity in one direction or the other. Or maybe my function has a wild oscillation. And if you need to review those things, you can go back into chapter 2 of the textbook and review them. But this is kind of, I think, what we all first picture when we think about a limit that doesn't exist. This thing that we ended up calling a jump discontinuity, because when the limit fails to exist, we can't be continuous, and it perfectly describes this case. Okay, well, I want to have this idea, but up a dimension, right? Now my domain is going to be 2D, right? I want inputs of x and y. I want to think about a function on two variables. And now this from the left and from the right doesn't make sense anymore, because now my domain looks like this. So I want to imagine I have a function graphed in space, and maybe z is this dome, right? It's a hemisphere that's been shifted up the z-axis, right? And so its domain is this purple region of the plane. And let's just, for convenience sake, identify a point here to be x naught, comma y naught. And so we're going to think about the limit as xy approaches x naught, y naught, for what I'm thinking about is some function who has domain this closed circle in the plane. Now, it doesn't really have to be this particular function. I just want to think about something graphed above, right? That z-axis coming straight out of the board. Well, this idea from the left and from the right doesn't make sense anymore, because there are a lot of different ways to get to the point x naught, y naught. Any path in the domain would be a path, a way to do it. So we could go on this straight line path, either this direction or this direction, or this one. Or we could take a parabolic path to the point x naught, y naught, right? There are infinitely many different paths that go through that point. For the limit to exist, we need something like this, where no matter the point I was going through, right, the z's are all ending up in the same spot, right? So in a parabolic path or a linear path, we're all getting the same thing. We're not ending up with a situation where there's a hop, break, skip, or some kind of infinity going on in the z direction. So to create this idea, what I need is the idea that I need to look at different paths. I'm looking for a test for the non-existence of a limit, really. So in the case where the limit exists, it means every path through the point has the same behavior when I graph the function. If I can find two different paths where I have different limits along those paths, well then that's the analog to this, right? Because I have two different directions to go and I got different values. It's a little more difficult maybe to think about, but if I can find two paths in the domain of f of x, y, z that make this limit do different things, then that limit will fail to exist. This is called the two-path test for the non-existence of a limit. If a function z equals f of xy has different limits along two different paths in the domain of f as xy approaches x naught, y naught, then the limit as xy approaches x naught, y naught of f of xy fails to exist. So let's look at an example of that. So I want to consider the function f of xy equals x squared times y all over x to the fourth plus y squared. And I want to show you that this function's limit as we approach the origin does not exist. And so I brought along a graph of this function to look at, because as I approach the origin, I can kind of see that, and of course, this is a GeoGebra graph, and GeoGebra can't actually graph all of the function, right? Because I see that I'm not allowed to plug 0, 0 in. I'd get 0 on the bottom, so this should keep going up this kind of parabolic ridge, right? It should get closer and closer to the z-axis. And I kind of think I see what's going on, right? It looks like sometimes when I get really close to the origin, I'm higher than other places where I get really close to the origin. So if I imagined tracing out a contour curve on my surface, right, I'm getting closer to the origin if I thought about the shadow of this curve in the domain, and I'm kind of low on this ridge. Please excuse me, I missed a little bit there. And then if I was to kind of go up here, I'm going higher towards the z-axis, right? It looks like different paths in the domain would result in different contour curves on the function. And so for our paths in the domain, you can think about what would be traced out on the function. So, well, how do I use this two-path test? I want to think about different paths. And so, since in this diagram, parabolas seem to be having different results, I'm going to look at the path y equals x squared in the domain. I want to think about what this limit is doing as I get closer and closer to the origin along this parabolic path. Well, what's nice about that is that reduces our limit. This limit statement on the path y equals x squared is a little easier, because on this path, x comma y gets closer to 0, 0 when x gets closer to 0. Because when x goes to 0, so does y. And along this path, well, y is equal to x squared, so on top I end up with an x to the fourth. And on the bottom, when I plug in an x squared, I would get x to the fourth plus x to the fourth is 2x to the fourth. And I end up with 1/2. Okay, so I ended up with 1/2. Let's look at another parabola, right? One path, a second path. Again, now my parabola is this one as I get closer to the origin. X and y both tend to 0 now at this when x tends to 0, right? Because if x goes to 0, so does y. Substituting in the x squared, I'll get a minus x to the fourth on top. Squaring x squared on the bottom, I'll end up with a positive 2x to the fourth. And this limit goes to minus 1/2. And so what I see on this side is a path going towards minus 1/2, which is almost right here at the top, right, of what GeoGebra's graphed so far. And on the other side, on that parabola x equals minus 1/2, excuse me, y equals minus x squared, I'm going towards minus 1/2. I have my two different paths with two different behaviors. So, the two-path test implies that the limit up here does not exist. Now let me show you a way to do this without writing down two explicit paths. And in doing this, we'll see something that's even cooler about this function. The limit is xy approaches 0, 0 of x squared y over x to the fourth plus y squared. This time, instead of just thinking about two different parabolic paths, let's think about them all. Let's let y equal k times x squared, because that's literally all of the parabolic paths that would pass through the origin in the domain. Well, y goes to 0 when x goes to 0. So again, I've reduced this to a one variable limit along this path. Plugging in kx squared on top will give me kx to the fourth. On the bottom, I'll get x to the fourth plus k squared x to the fourth. I could factor out an x to the fourth in all of the places. And this limit goes to k over 1 plus k squared for whatever value of k we plug in. So literally, we have now infinitely many different paths. You plug in any k, we always get a different limit. So our two-path test here, any two paths would work, but this is a little more powerful. Now I know as I pick different parabolic paths in the domain, I always get different limits. And when I say different parabolic paths, what I really should be saying is different parabolic paths that pass through the origin. There are two important things about my paths. They actually have to go through the point, and outside of that point, be in the domain of our function. Okay. So every parabolic path that goes through the origin provides a different limit for this function. This limit super does not exist. There is one more thing we can notice about this problem. I should say at least one more thing we can notice about this problem. There are probably 50 other things we could notice, but only one that I'm going to talk about here and only one I'm thinking about right now. Let's say you were looking at this function on a lab test and you didn't graph it in GeoGebra, right? I came up with the idea of parabolas looking at this graph. Maybe we had the idea to try lines instead, right? All of the lines y equal mx go through the origin. And so maybe this is a way of generating different limits for different paths that go through the origin. Well, along this path, the same kind of thinking applies, right? If x goes to 0, so does y, so I'm getting closer to 0, 0, and my function becomes a one variable function, mx cubed on the top, and on the bottom, I end up with x to the fourth plus m squared x squared. All right, well, I can factor an x squared out of the bottom, and cancel it off with an x squared on top, leaving me with an mx and x squared plus m squared. Taking the limit, the top's going to 0 and the bottom's going to m squared. And along all linear paths that go through the origin, the limit is 0. And this is amazing. Literally every linear path has the same limit. Every parabolic path has different limits. So even if we try literally every linear path through the origin and always get the same limit, that doesn't mean the limit exists, because then we need to check all of the other paths. And so we need to think about what about this function might tell us to check the parabolas rather than the lines. And the trick is I need to be able to factor out that x to the fourth and cancel it off with all the powers of x on the top. And so thinking about the degrees involved might have led me to that x squared. And we could also talk about the common things we might try, like lines are a common choice, parabolas are a common choice. We might want to try the axes on some problems, right? The x-axis y equals 0, the x-axis x equals 0, and see what happens along our coordinate axes. But that's it for now.